This is problem 2 on practice exam 1 of chapter 1 in the book Problem Solving Guide for Differential and Integral Calculus. The graph shows total distance traveled as a function of time. For a 100-mile trip, you can imagine the trip odometer was set to 0, went 100 miles in a total of 2 hours, and every once in a while you plotted the distance traveled at a bunch of times, and you got this curve. Part A is explain how you can read your speed from the graph. We have distance versus time. Where is the speed? The speed of an object is how quickly its position is changing. So most people say change in distance over change in time. This is only the average speed. The average speed over a time interval is the distance traveled during that interval divided by the duration of that interval. It's not the speed at any time. All right. If the speed of the car doesn't change much, if this delta t is really small, like a millionth of a second, then it's going to be the speed at the beginning of the interval, it's going to be the speed at the end of the interval, and it's going to be the average speed over the interval because the car's speed can't change much in a millionth of a second. So we want a representative speed. We have to keep the times close together. So let's explore this a little bit by getting the average speed over the first hour. The average speed over the first hour is the slope of the line that connects the beginning and the end of the interval. So let's put a dot at 0 right here, and let's put a dot at 1 hour. The rise, let's connect those points. The rise is the distance traveled, right? The run is the time taken. So the slope of this line that connects the 2 points is the average speed over the interval. So it's 40 miles in 1 hour. The rise is 40 miles. The time is 1 hour. That's the average speed. That's not the speed at the beginning. That's not the speed at the end. That's the average speed. So how can we get the speed at a particular time? Say 1 hour. How fast is the car going here? We can calculate the slope between 2 points that are very close together. Here's 2 points very close together. The line that connects these points is going to follow the actual line for the distance traveled very closely because they're very close together. And if we keep on getting them closer and closer together, delta x is the distance traveled, delta t is the time taken always. It doesn't matter how big or small they are. We can get the tangent line. The tangent line is, the slope of the tangent line is the speed at a particular point. So there's a tangent line. I don't know, what's that, 58 miles? This looks like 21. That's 37 miles over 2 hours. The run is 2 hours. That's like 18 and a half. The slope of that tangent line is the speed at a particular point. So the answer to part A is, to get the speed, you get the slope of the tangent line. And there's a lot of calculus ideas we just talked about. So to get the speed of the car at 45 minutes, we need the slope of the position versus time graph at 45 minutes. So we identify the point right here, 0.75. We need the rise over the run at that point. We draw a tangent line. And what is that, 53, something like that? This looks like 25. That's a rise of 28 miles in 2 hours. The average speed is 14 miles an hour. You probably run into some traffic. There'll probably be some construction going on. Now let's look at part C. Half an hour into the journey, is the speed increasing or decreasing? More deep calculus ideas. What's happening to the slope at a half an hour? That's the question. If the slope is increasing, if it's getting steeper, the speed is increasing. If the slope is decreasing, the speed of the car is decreasing, and that slope is decreasing. It's steeper here than it is there. It's steep here, and it's getting less and less steep as we go this way. So the car is slowing down. All right. Were you exceeding the speed limit? Part D. Where is it the steepest? Where is the distance changing the most in time? It's pretty steep here, but I think it's probably steeper here, somewhere in here, maybe 1.5 hours. That's pretty steep. So we put a point there, put the tangent line there carefully, and we get the slope of the tangent line. So the rise is the whole span, 100 miles. The run, what's that, 1.8 something? 1.92, 75, 8, 85, 90, 95. Yeah, 92. And this looks like 0.5, 0.55, 0.6, 0.65, 0.63, okay. 100 miles in 1.29 hours. The run is 1.29 hours if we're careful. Ooh, 77.5 miles an hour. Speed limit's only 70. You're exceeding the speed limit at 1.5 hours. That's problem 2.